way, if they're in the background and so on, we won't hear it. And it's more than one of you in the room, please send Sarah or I an email just saying there were and so on. We like to keep track of who's just for count. And Sarah, when you're ready, we can go ahead and get started, and we'll have, we're starting a few minutes late, a sort of 45, 50-minute presentation, and for a few questions at the end. Thank you.
I don't know whether it's good morning or good afternoon, because I think they're all in different time zones. Hoping that you can hear me fine. So what I wanted to talk today is about AMOC variability and mechanisms in both fully coupled models and in forced hindcast ocean simulations. So work is done at NCAR, and some of it is especially involving many other people, but primarily a postdoc from Texas A&M University. So I would like to acknowledge Steve Yeager and Lendron's contributions from NCAR. So next. I wasn't quite sure about the background, and the instructions indicated that maybe I should provide some background. So on that topic, I want to briefly touch on why we care about AMOC by focusing on its role in climate and climate variability. I could briefly talk about representation of AMOC variability without getting into mechanisms that much in coupled models. And I looked at the NAVIS sort of early career scientist list. I thought that you guys be interested in two things. So from the modeling side at least. So that's why I structured the talk into two parts. The first one is the impacts of ocean model parameterizations on AMOC within the Community Earth System Model, CESM. I can get to the essentially recent effort Atlantic simulations in what we call coordinated organized reference experiments, second phase of that thing, and that's focusing on intraannual to decadal variability and trends. These are hindcast simulations. This is almost you've probably seen various versions of this particular showing the simplified sketch. It's a simplified sketch of the global overturning circulation system. This particular one is from Coolbert et al.'s review paper from 2007. And the goal here is actually, this may be preaching to the choir, that we are dealing with a complex circulation system. Among basins, you can see that the circulation is essentially extending from north to south, particularly in the Atlantic Basin. And Atlantic actually has two of the major deformation regions in the Nordic Seas and in the Labrador Sea region. Next. So, okay. When we talk about AMOC, essentially, we are simplifying further the simplified schematic. And on the right side is the representation of AMOC mean state from one of our simulations. The top one shows the global overturning circulation. So it's a further simplification is coming simply because you're forming a zonal integral. The contour levels indicate clockwise circulation in this view, and negative ones indicate counterclockwise. And I'm going to look at the AMOC distributions or variability in primarily depth, latitude, space. So then the bottom panel, the bottom lower right panel shows the AMOC, essentially Atlantic meridional overturning circulation. So the point to make here is that of the global overturning circulation, majority of it essentially is associated with the circulation that's in the Atlantic. And positive circulation patterns are associated usually with North Atlantic deep water, and then the lower part, that region in the is associated with the Antarctic bottom water circulation. We care about AMOC. The next, please. The next slide. And usually I can skip these. I have only a few slides to just justify why we care about AMOC. Bottom observations, as from rapids and from modeling studies, we know that the majority of the northward heat transport that has significant impacts for the climate is associated with AMOC, roughly 90% of that. And this is showing a plot, regression plot from a recent paper from Rimas, the lead author. The blue are the rapid observations, and the other colored lines or dots show this CSM4 oscillations. You see that the AMOC strength for the northward transport directly relates to the AMOC strength. It has implications, of course, for the climate. Next, please. Another connection related to AMOC, although it's with model evidence, is coming from the Atlantic multidecadal variability, AMD, also referred to as Atlantic multidecadal oscillation. This is from Sutton and Hudson, the top panel showing index. It is essentially representing the sea surface temperatures for the North Atlantic. It's low-pass filter, and some kind of trend is subtracted. What you subtract, essentially, what kind of trend you subtract will impact some of this details. But anyway, you get a picture of some kind of low-frequency variability, although observational records from STs are very short. And if you actually take the ST time series and regress onto AMV, then you get the bottom panel, which is a hemispheric signal in terms of the SST. In this case, it's warming, particularly on the Atlantic basin. Next. We know that, from various studies, this warming seas in the North Atlantic is associated with various climate impacts in the surrounding regions, both in the Atlantic basin and surrounding areas. For example, drought conditions in southeastern U.S. perhaps, and rain in the African side. And associated also with this east hurricane activity, but not so much with the warm seas. It's coming from the changes in the shear in the atmosphere. Next, please. Evidence, essentially, we need more observations of AMOC and all the related fields. So in the absence of long and continuous observations, the model see that the AMOC, essentially, changes in AMOC lead the sea surface temperature or AMV changes. So that is essentially a link, a model-based link showing the AMOC relationship to sea surface temperature anomalies. Although there are some recent studies indicating that perhaps for AMD, dynamics is not really important. Next, unfortunately, rely on models in the absence of observations. I just wanted to show the sort of non-robust elements of representation of AMOC variability. These are AMOC index time series. Of course, I had to include the NCAR model, but I just chose two additional representations. The top panel shows a time series from one of the GFDR models, CM21. The middle shows time series of an AMOC index from CCSM3 and CCSM4. And the panel shows an AMOC time series, the top line in the bottom panel, from a German model, MPI You see that the model, the AMOC, for example, variance and the time scale of variability differs substantially among the models. GM21 had almost a locked-in variability about 20 years. In the bottom, you can see centennial time scale variability. And in CSM versions, we have seen different variability characteristics. One particularly interesting one is the representation in CCSM3. So you can see that after the initial sort of adjustment, we have a 3 period with rather 20 to 21 year oscillation, then it essentially changes to a red noise-like spectrum. Of course, with the model, you can essentially come up with various explanations to explain both the time scale and why this is happening. Next. If you look at literature, for each model almost, there is, I'm a little bit exaggerating here, but there's quite a substantial spread of variability mechanisms that are included in literature, and they are substantially different from each other. And without getting into detail, I sort of listed some of the issues and variability mechanisms here. I wanted to come in the previous plot that the amplitude and time scale of variability differ quite a lot among the models. Proposals include, for example, changes in the ITCZ, of ITCZ, and that impacts salt transport, for example, changes in the deep water formation zones in the North Atlantic, and some studies indicate there's a seesaw pattern between the Nordic seas and the Labrador Sea. Involve freshwater transport to and from the Arctic Ocean and Nordic seas. There's also, depending upon a representation of the primary the atmosphere, either the East Atlantic load or NAO, that's the North Atlantic Oscillation, may play a role. And these also, along those ideal lines, say that essentially the Southern Ocean is dictating what's happening in the North. Issue of model variability, again, quite model dependent. Some models show coupled, some models show ocean-only transportation. And Nixon interactions also are both. In some cases, the variability or changes in the Pacific tend to lead the Atlantic basin. And as I said, the role of although most of the recent studies point to some prominent role to persistent, for example, phase of NAO, positive phase, the role of North Atlantic oscillation remains unclear somewhat. And the roles of model mean state biases, model resolution, particularly, for example, Nordic Sea overflows, and ocean model parametrizations remain quite unexplored in my view, and there are many non-robust elements. Next. So, and could you put one more? There's a circle, it should appear. One more return. Okay, I just wanted to point out that the biases, these are showing the sea surface temperature on the left, and surface salinity biases from observations, mostly climatological world ocean database observations. You can, these are two different CCSM simulations, CCSM4 in the top and what we call ensemble control simulation. These are pre-industrial conditions, but I mean, no matter whether you look at present day or not, you get pretty much similar biases. The largest biases that we have in the coupled system, you see that that is actually located in the North Atlantic. Especially the sort of coarse resolution models that we use in the climate simulations, or 1 degree or half degree or even quarter degree, they really properly get the Gulf Stream separation correct, and the subsequent path of the North Atlantic current is not right either, and then up with the cold and warm bias structure in the sea surface temperatures. And this is a long-standing model bias issue. And it is unclear how this bias, for example, impacts AMOC variability, and perhaps more importantly, the precision and predictability of, for example, climate on decadal time scales. Next, please. The representation of the overflows matter a lot. More hit return. I mean, we have deep water formation occurring in the Nordic seas, and they essentially get into the Atlantic through two relatively narrow channels. One is Denmark Strait. The other I just labeled it as a single one, Periodan Channel, but there are multiple passageways into the Atlantic basin. And not only getting the right water masses forming in the North Atlantic, in the Nordic seas, the important thing is essentially getting overflows correct with the first entrainment, and the models that are used today, mostly they are level coordinate, z-coordinate models, and they're notorious basically because of their numerics and steady topography, not to essentially have the proper representation of the Nordic Sea overflows. To run those mini groups do different things. The common thing to be done is essentially you just dig these sills very deep enough that so that eliminate kind of bottom topography, so that you can essentially have direct flow from the Nordic Seas into the North Atlantic, but it impacts essentially your time scales and everything. So the ocean model, what we have is based on our collaborations with James and collaborators, we have developed an overflow parameterization, it's a duality model, to overcome some of the issues that I just mentioned with the z-coordinate models. We essentially use a stream-to model. That means, for example, source waters and the transport of the source waters, you can just follow the coastline, is in a sense handled through stream tubes through the actual rocks in your model. Of course, I mean, you are not, it is a conceptual rock flow model in a sense, flow through the rocks. But we essentially parameterize the source water formation, and entrainment is parameterized as a single point entrainment model. And in the end, we produce a product model that can be inserted at whatever the model wants to do with reduced excess spurious entrainment that they otherwise had. Next. Maybe 3-4 times here. Okay, one more. Okay, so in the absence of long and continuous observations of AMOC and related variables, we don't have them available, and that's why we need also continuing observations. Both cold and uncast ocean simulations remain as essential tools for studies of decadal AMOC variability, mechanisms, and prediction. And it's very important that we understand, for example, why such variability, a particular variability is occurring, what's happening, and because that's important for decadal prediction simulations as well. And we should be able to identify robust and non-robust elements. So in this part, I would like to just show you some examples of a sensitivity of AMOC variability to some model parameterization. So I'm presenting in that case a systematic assessment of the input of several ocean model parameter choices and comparing those changes to atmospheric initial condition perturbations on AMOC characteristics in ESM ocean model. And this to identify some robust and also non-robust elements of AMOC variability mechanisms. Next. So what I'm going to show you is what I've done is actually I've performed several long simulations. These simulations, I have actually modified or changed some loosely constrained parameter values in the ocean model. This is not necessarily, I mean, just CESM. So these parameters are set in an ad hoc or loosely constrained manner in pretty much all of the ocean models. Not pretty much, all the ocean models. So one, for example, vertical mixing parameterization. We've changed the background mixing from 0.17 times 10 to minus 4 to 0.1 times 10 to minus 4 meters per second. These are all defensible based on available observations because, unfortunately, observations are rather difficult and they provide a range of, for example, mixing parameterization value, parameter values. And even though it may be okay to get a factor of 2 or 3 spread in the observations, another point that I would like to make here is that a factor of 2 to 3 spread in the observations can make a huge difference in the model simulation. So that, I guess from the modeling point of view, observational spreads need to be narrowed down to the extent possible. important, for example, change that I made is the sub-mesoscale mixing parameterization. Essentially, these are all subgrid scale processes, and essentially some process model and studies. And in example, sub-mesoscale mixing parameterization, there is a specified parameter representing the width of the mixed layer fronts. And the difference is that length scale should be between 200 meters and 5 kilometers. And versions of the model, I set that into 5 kilometers, and pretty much in the whole world, that 5 kilometers is being used now. I changed that thing to 3 point, reduced it by essentially 33%. And I need similar changes, for example, in the mesoscale parameterization. It increased the deep mixing values from 300 to 600, and also reduced the upper ocean values of the mixing coefficients from 3,000 to 2,000. Again, these are all reasonable changes. And horizontal viscosity parameterization change, I reduced it. And at baseline, sort of, I also wanted to compare these things to if I do some random really perturbations, initial conditions, round-off level, what happens. So I can compare it to this set of parameter changes to those. You can also view these experiments as essentially, especially the last initial condition perturbations, as either extending the integration length. So in other words, the AMOC variability is non-stationary in a sense. I showed an example in the CCSM3 simulations. So next, so we don't have to spend too much time on this, but we have a long control integration as the red line of the order of 2,200 years. So looking at that, and then perturbation experiments, sensitivity experiments that I listed on the previous page are given here by the blue lines. They start from year 402, that's sort of a semi-equilibrated state of the large ensemble, what we call control, or long control. Each of the perturbation experiments are run for 600 years, so they are relatively long. And then the other experiment at our disposal, that's what we call last millennium simulation. It has the same ocean model, 1 degree ocean model, but its atmospheric model resolution is 2 degrees as opposed to 1 degree. And what is essentially annual mean outputs, unless otherwise noted. And these are going to be also, many other AMOC indices, I'm just using the 45 degree north index and 10-year low pass filter. Next, please. This is to show the AMOC mean states. These are 50-year means. The upper left is showing the AMOC state, mean state, from the control simulation. The panels are showing the differences from the AMOC mean state in our perturbation experiments. So for the bottom row shows the initial perturbation experiments. You see that the mean state does not change much. And the other cases, the two cases with most of the mean state change is what I labeled as MUO and MUO. Those are in the middle rows. They involve changes in the mesoscale mixing parameterization. Now, one case, that's SM. That's what I was discussing. That's the sub-mesoscale mixing parameterization, and that's the length scale change from 5 kilometers to roughly 3 kilometers. You can see here that there is minimal change in the mean state of AMOC, and I'll come back to that in a few minutes. Please. These are mean and standard deviation distributions, so scatter. All of the experiments are given here. So the thing that I wanted to point this thing out here is that in the past, there were studies indicating that the AMOC variability is depends on the AMOC mean state. And particularly, the larger the mean AMOC, the standard deviation or variability seems to be larger in some models. What we are seeing is essentially in these CSM simulations, we do not see any clear relationship between the AMOC mean state and variability. And you put that the green right there is the one with the sub-mesoscale mixing change. So there is not much change in the mean compared to some other cases. but you can see that the variance or the standard deviation is quite large in that particular simulation. Next, please. And the AMOX index power spectra. So now you can what is shown here is the dots are 95% confidence level, and pairs are the 90% confidence level. I use sensitivity experiments in the top panel. The bottom panels show the impact of the initial atmospheric perturbations. The black is, in a sense, in all the cases, is the same. That's our control, 2200-year control. But you can see that just by changing simple in the ocean model, and they are all loosely constrained parameters, and I can defend all of these parameter choices, you can see substantial differences. You can get substantial differences in variability. And again, I want to point out that SM case, that's the blue line in the top panel, left panel, you can see huge variance. In that case, there is actually pretty regular oscillatory behavior of the order of 30 to 35 years, I believe, in AMOC. And note again that AMOC mean state did not change. We simply changed the variability and time scale of the variability. And you get also the bottom panel that shows the AMOC initial condition perturbation experiment. And the bottom line is that, especially at the bottom panel, is that the AMOC variability is not necessarily stationary. So if I could have done the same experiments and just run them longer, and likely AMOC variability would have changed. So let's go to the next panel. And now I want to get back to overflows, because that's a major sort of numerical issue. And in the past also, people argued that the change in the source water properties of the overflows can impact the AMOC variability. In fact, some models, I'll show an example on the slide, show direct link. And we are finding in these experiments, the top panel is a scatter plot of AMOC index versus the total overflow product water. So it means, if you look at it with some pink glasses, perhaps, or whatever shape, you can see some kind of relief. Perhaps the larger overflow transport seems to impact the mean transport of AMOC. But more importantly for variability, in our simulations, we are not seeing essentially any leading role for the overflows. If you look at the AMOC standard deviations, there is no direct link between the higher variability of the overflows and the higher variability of the overturning circulation. Now, one more return. This is intended to show the lead-lag relationship between AMOC transport and the overflow product water. The top panel is from these experiments. The solid black line is showing the ensemble of all of those, and then the gray shading is the spread. So in our cases, actually, we do not see any lead relationship for the overflow waters. This is with the bottom panel. This is from the HAD-TM3 model. You can see that in that case, overflow was leading. So, I have several issues with that particular model, but more importantly, they've done a lot of, I believe, digging of the Mark Strait and Fairbank Channel region. So in that case, whatever is happening in the further north is directly impacting, it has a really artificial path to the North Atlantic. So I believe that's the reason that overflow changes are leading in some models. And in other cases, that is not the case. Next, please. So in others, and in many of the other simulations, the Labrador Sea is emerging as one of the regions leading changes in AMOC. What is here is the upper ocean density that's in color, and mean boundary layer depth regressions onto our AMOC index, and in this case leading by 3 years. So you can see that I just marked that region with the red region there. What's happening in the Labrador Sea essentially, increased buoyancy, increased density, and the mixed layer depths tend to lead changes in AMOC in pretty much all of our simulations, and that's also happening in many other now coupled model simulations. Next, please. to do now is essentially, we know that the AMOC variability amplitudes, for example, and the time scale vary quite a lot among the models. And I'm to identify some robust aspects of AMOC variability that we can hopefully count on. What I'm showing here is the AMOC index correlations with boundary depth, the top right, top left, the lateral C density, upper ocean density, all computed in that box region. Solar transport and NAO, those are the two bottom panels. Again, the black is the ensemble mean, and the shading in each page indicates spread among the minimum maximum ranges among the models. So consistently, what we are seeing is essentially large cities lead to larger boundary layer depths in the Labrador Sea region. In turn, essentially is leading AMOC changes in our models. You can see also a simultaneous relationship between the subpolar strength, but in this case, it's essentially in a sense response to action to some degree. And we also see a leading role for NAO in this case. You can see that the correlations are peaking roughly 2 to 3 years prior to an AMOC intensification. But I should mention that the AMOC is leading for positive lags in the odds. And I'm not going to get into detail, but essentially NAO is influencing the deep water formation through it is buoyancy fluxes, not wind part essentially. It's primarily associated with buoyancy fluxes. Maybe? So another thing here is that, as I said, the densities are large prior to an AMOC intensification. And there has been also some debate about, well, what is causing that increase? Is it due to temperature changes or is it due to salinity changes? And if you look at the models, you can come up with different explanations. So what I'm showing here is now same density plot as before, but for some of the individual cases. Gold is shown in black, blue temperature contribution, red is the salinity contribution. So as I said, the robust element before was the increased density in the Labrador Sea prior to an AMOC intensification. Now we see that for negative lags, that increase in density can be due to high temperature. For example, that's shown in panel 00, the temperature is shown, for example, in the first panel in the upper right, or it's dominating in case 001. But in some cases, it's dominated by salinity, but in some cases also, it is almost an equal contribution from temperature and salinity. So we cannot really robustly say when the density is increasing in the Labrador Sea, it's due to just temperature or salinity. It's quite model dependent, and not only that, it's a non-stationary feature, at least in our model. First, however, afterwards, we see in all the cases density is getting reduced after AMOC intensification. That's the initial positive lags. And in that case, while salinity contributions try to increase density, temperature is the primary driver in that case to reduce density. In all those cases, we are seeing actually taking temperature into the Labrador Sea is reducing the density anomalies. Next. So this one, I've skipped many budget analysis, but I think it's going to be too much material and confusing. Both the amplitude and time scale of AMOC variability differ considerably among the experiments, with dominant time scales of variability ranging from decadal to centennial. Differences in details of how the density anomalies leading to AMOC changes come about, but rather than focusing on the non-robust elements, I try to focus on robust elements. The 3 CSN simulations, pretty much in all of them, we are seeing the Labrador Sea as a key region with upper ocean density and boundary layer anomalies preceding AMOC changes. We see a driving role for Nordic Sea over transports in terms of variability. I just want to be clear, not for the mean, but just for the variability. At AMOC intensification, subsequent weakening is due to advection of positive temperature anomalies into the deep formation region. I'm not show them explicitly, but what we are finding is that, in some sense, in quotes, persistent NAO is playing a significant role in setting up the density anomalies that lead to AMOC intensification via buoyancy fluxes. Part 1, it was related to coupled models. Now I'd like to switch to part 2. Next, please. This recent study, this paper is in review, and I wanted to tie this part with this part in terms of mechanistic understanding. So we want to now focus on the North Atlantic simulations in a set of coordinated ocean ice reference experiments. We refer to them as Core 2. It involves essentially pretty much all the modeling centers, ocean modeling groups from around the world, and they are listed here. Next, please. One more time. For those of you who are not familiar with what Core 2 is, it's an experimental protocol for running ice-ocean coupled simulations forced with intraannually varying atmospheric data sets for a 60-year period from 1948 to 2007, and it's supported by or coordinated by our Ocean Model Development Panel. I mentioned that I'm thinking that you guys may be interested in using these simulations or performing some ice-coupled experiments to understand mechanisms, for example. That's the reason for this part of the talk. And we think that these simulations, these high-gas simulations, provide a nice framework for evaluating, understanding, and improvement of ocean models. They're used for investigation of mechanisms for seasonal, intraannual, and decadal variability. They used to evaluate robustness of mechanisms. And I also think that they complement data assimilation and bridging observations. I point out that they are being used to initialize decadal prediction simulations in many decadal prediction simulation or decadal prediction groups. Just a brief summary of the protocol. We have models integrated for 300 years. This corresponds to 5 cycles of the 60-year floating period. We assess the degree of equilibrium achieved and then analyze the solutions. One major caveat, however, is that the participants are free in their choices of ocean parameterizations, diameter values, surface freshwater, and salt flux treatments, ice models. So they can use essentially whatever salinity restoring that they are comfortable with in these experiments. Next, please. If you are, this is now the Core 2 framework, and the protocol is an endorsed MIP within CMIP, so it's an OMIP, designated OMIP. If you're interested, you can look at the web page that's listed there for data sets and documentation, and actually creating, in fact, 2 papers, right now there are about 6 or 7 papers already accepted, the ocean modeling Core 2 virtual special issues. So you can take a look at those papers as well if you're interested in. Next. So I wanted to cover here briefly, very briefly, is that we essentially wanted to provide an evaluation of how participating models represent trends in variability in the Atlantic meridional overturning circulation and other fields on intraannual to decadal time scales. We are trying to identify robust aspects of AMOC variability in the presence of mean state differences. And again, I wanted to explore AMOC variability relationships that I showed earlier with NAO, layer depth or boundary layer depth, and Labrador Sea upper ocean temperature, salinity, and density. And this is essentially part 2 of our earlier study that was published in 2014, looking at the mean states from these models. Next. So the groups, they represent pretty much all of the ocean modeling groups around the world with different coordinate systems and nominal 1-degree resolution, all the models, pretty much. Next. Only the analysis from the last 50 years. Annual mean fields again. Anomalies are with respect to those 50 years. And a 7-year cutoff is used here. And again, we looked at AMOC in density space as well, but most of the things that I'm going to show are very similar in depth space. So I'm focusing on depth space AMOC. Next. States. And you can see that even though we are using the same atmospheric data sets, to force these ocean models, you can see quite widespread among the models in their mean state representation. Some models have really strong North Atlantic deep water, some models have really very weak, and that also impacts the representation of the anti-bottom water cell, that's the negative bluish cells at depth. And next, please. And I thought this plot, this is showing the comparison with the rapid data set, that's the black line. And since we cannot provide a direct observational comparison of that AMOC structure that I showed on the previous plot, we can compare it to available rapid data set. Here for the models, black is the rapid in all panels, and you can take a look at your favorite model and show or see how it compares to other models and also to rapid. Because most models tend to underestimate the AMOC transport, and you can see a persistent model problem here again. The representation of the North Atlantic deep water, that's directly linked to overflows essentially. Because of excessive entrainment in most models, the North Atlantic deep water penetration that remains rather shallow, and that's represented by the zero crossing of the overturning of the profile. So I'll just advertise with the blue one in the top left, and it does that relatively well compared to rapid, and you can see some deep Atlantic deep water penetration in this measure. Next, please. Top maximum transport time series is getting into some variability. 26.5 and 45. 26.5 was chosen because rapid is there. That's shown by the black line at the end. It's a very short period, of course, in this comparison. And the 5 north is sort of representing the mid-latitude AMOC variability. You can see quite differences among the models, but you can essentially see common features as well. We see low AMOC low anomalies during till mid-70s, then AMOC intensifies till about mid-1990s, and we are seeing essentially a decline in AMOC transport. Compared with observations, these features, but comparing to other ocean model simulations forced with different data sets, we do see a similar behavior in AMOC representation. Next. These are correlations. In other words, when we force the models using the same forcing data sets, how well do they essentially represent variability at various time scales? So again, the top panels show 26.5 and the bottom is 45 degrees north. The side is the high pass filter. So if you look at those, we see quite a bit of correlation among models in their representation of low high frequency variability. That's directly linked to essentially momentum forcing. And the exception is the data assimilation. I don't want to get into detail, but it has problems. Then the remaining panels show essentially low pass filtered with trend and low pass filtered and detrended. So this is actually indicating that at frequencies, buoyancy forces, essentially forcing becomes important, and it feeds into how the models form their deep water formations. And you can see more discrepancy in the low frequency variability among the models, and it's also indicating that most of the agreement among the models is coming from the representation of trend. Next. This is one spatial distributions. Again, no detrending is applied. To us, actually, this was a surprising plot, because if you look at it, you'll see that some models represent AMOC variability primarily focused in the North Atlantic, while others essentially show little variability in the North Atlantic, and they tend to put the maximum variability southern hemisphere. In a simulation case, that variability is concentrated in the sort of equatorial region. This actually sort of makes the I mentioned that if you look at a similar plot from reanalysis products, you get similar diversity. So we should be cautious when we essentially use these simulations, and particularly not just these, but also reanalysis products in initializing decade prediction simulations. Next, I'm going to show the time series because it's very similar to what I showed. So next, please. One is that the sea surface temperatures, that's essentially representing A and B, is represented quite nicely in the models. This indicates that essentially it's dictated by the surface forcing. Have these observations that ISST is given here in the black line, and you can see quite a bit of agreement on models and their agreement with the observations. This agreement that we get the sea surface temperature spatial distributions the same in all the models. So what is here the sea surface temperature EOF distributions. The lowest in the bottom row, the rightmost panel is from the observations. So you can see quite a bit of a difference in sort of the extent of the, let's say, the positive anomaly and the magnitude of it among the models. This is directly related to the individual models, essentially dynamics or representation of the ocean circulation. Next. I just wanted to show you this one plot. This ties now this section to the previous section that I talked about. One application of this, for example, these simulations is essentially, we can again look at some robust aspects of AMOC variability. We caveat that the time series that we are analyzing is very short, and some of these statistically may not be very significant. We are looking at it right now. These are low-pass filtered AMOC maximum transport time series correlations with, again, Labrador-Sea mixed layer depth. We don't use boundary layer depth in these cases because every model has a different thing. They don't necessarily do the boundary layer, but we use the mixed layer depth. Tropic stream function in the subpolar gyre, pseudosine in the subpolar gyre, and NAO. Here, again, positive lags, AMOC is leading. Each row, column essentially represents these models that are given in the figures, and black line is the multi-model mean of those lines. So of course there are exceptions and differences among the models, but if you just look at for example, the top row and the line, you can see that in these simulations we're seeing a leading role. I show the density here, but the leading role for the mixed layer depth deepening prior to AMOC intensification. See that in the barotropic stream function almost simultaneously correlated. Of course, the correlations are negative. And I'm seeing again in these simulations a leading role for NAO prior to an AMOC intensification. And this is actually consistent with what I've tried to lay out in the previous section. Mixed layer depths and a leading role for NAO through buoyancy fluxes. I'm going to get into detail here. Okay. Okay, now here, this is the summary for the part 2. Variability shows 3 distinct stages. This is consistent with the results of previous studies that use a variety of atmospheric forcing data sets. And of course, we cannot necessarily confirm it from observation. So that's why the key message here is we need more observation. For the previously identified variability mechanism where positive density and mixed layer depth anomalies pre-AMOC intensification, these relationships show that both mixed layer depth and NAO indices lead AMOC about 2 to 4 years. Correlations tend to show general agreement in their representations of AMOC sea surface temperature and subpolar mixed layer depth variabilities. In particular, the time series of A and B is captured in a sense rather well by the models. Perhaps this is not surprising. It's dictated by indicating that forcing in a sense. So, of course, despite these general agreements, there are many differences among the model solutions, particularly the spatial structures of AMOC variability. For example, the location of the maximum AMOC variability differs among the models between northern and southern hemispheres. So, stop and take any questions that you may have. Thank you.
Thank you, Gokhan. That was big. So, get up to questions. So this is the time to unmute. Any questions for Gokhan?